Construction University, and we are indeed very honored to have him speaking here today and serving as a judge. His talk will be on chips and channels, our journey through concurrency and parallelism. Without further ado, please join me in welcoming Jason.
Thanks, Jesse, and I'm pleased and honored to be here participating as a speaker and as a judge, and particularly honored to be an alumni of both institutions, so it's a great confluence of things. As Jesse mentioned, if any of those things are interesting to you, those capacities I've served in, please kind of approach me after and find out more about that. I don't want to dwell on it too much. Right here, we'll just kind of launch into the talk. The title of the talk is Chips and Channels, as was mentioned, and Bill Kennedy was kind enough to kind of lay a lot of the groundwork for the concepts behind what is parallelism, what's concurrency earlier in the day. So hopefully I'll be able to get through a lot of these examples that I have in this talk much more quickly to have that knowledge base already firmly in hand. So this talk will actually cover hardware and software because I've done hardware development for IBM across application-specific chips, processors, and memory. And I'm also working in software at this point. So let's get started. So here's just a quick origin story, and I covered most of these points. So the goals for this talk, basically got two. I want you to gain a feel for both concurrency and parallelism with examples. Three of those examples are going to be hardware related, but you'll see that obviously how software functions on those systems has a lot to do with how you manage concurrent and parallel operation. And I want to draw analogies from hardware to distributed systems architecture as a result of working through the 4 examples. So Bill put this up earlier. Actually, this is a lot of the information on this particular slide is from the talk shown at the very bottom bullet on the slide, which is entitled Concurrency is Not Parallelism. That's by Rob Pike. And Rob's actually one of the inventors of the Go programming language. He's basically on the Go team, essentially, that ideated the entire language based upon previous languages they had seen and the challenges that Google was seeing in terms of writing their software at scale that Bill mentioned in his talk. So, thanks Bill for bringing up these points. I'll go through them quickly one more time though. In Bill's talk, there were basically 3 things I wanted to point to. He talked about the way in which you can manage parallel operation in essentially on an operating system thread with the Go runtime, right? And so one of the ways was with Go max procs, the other was with wait groups, and so forth. So those are at least 2. We'll come to another one kind of later on in the talk. The idea is to be able to put points of coordination in on otherwise independently operating parallel activities. That's what concurrency is all about. It's about structure or coordination of parallel operations. Parallelism itself, without any coordination, is just the simultaneous operation of possibly related processes. And this is actually, these are Rob Pike's statements sort of paraphrased. The third bullet down, basically, I want to point out that if you look in the source code for a program, and those examples got into this in some pretty good depth, parallelism that exists away from the points of coordination doesn't guarantee that at runtime you're going to have parallelism, right? The point is that it isn't necessarily the case that when your code is running on the machine, it's going to map to a ton of parallel resources that are already all freely available. Even if semantically it's free to do whatever it wants, it's going to be constrained by what the hardware is able to execute. And some of the hardware examples I'll show kind of get into a few, at somewhat of an abstract level, kind of why that's the case. Anyway, I put a plug-in for Go here. Here's a number of very notable projects that either are written in Go or depend heavily on Go for the, the business model behind them. On the left, actually, I'm sorry, it's on your left, my right. You'll see Docker, Kubernetes. Has anybody got experience with either of those 2 projects? They're probably 2 of the most popular ones written in Go. Okay. Does anybody understand what this one is here? See this symbol here? I'd like to introduce you to it today. It's if you've ever used Amazon S3, this is the Minio project, and essentially what it is an S3 clone. It's an API addressable object store, essentially, that mimics the S3 API. that allows you to write applications that don't depend on this huge monolithic S3 deployment that Amazon has, but rather you can put in place smaller groupings of actual physical storage for your objects to reside upon that tracks the size of your application. The one below it is a Cloud Native Computing Foundation project called Prometheus, and that's a monitoring project. So the idea, if you're interested in cloud native computing at all, one thing you'll note is that there are a lot of simultaneous things going on in the system. There's containers coming and going, there's, I would say, like serverless functions, there's service discovery and mapping. So basically, things are happening at random times for certain durations. There are various sizes, and they have various addresses associated with them. So it's hard to keep track of where everything is and what it's whether it's operating in a healthy manner. Prometheus is actually a database that's a time series database. It can be searched in a arbitrary way to get you some insight into a cloud-based system and how it's actually operating. Here we've got HashiCorp Vault, which is a secrets management tool that basically allows you to retrieve keys and other kinds of credentials to interact with databases and various things like that. If you want to understand how concurrent and performant and low profile a Go application is. Excuse me, I do have a cold, so just pardon my voice if it cuts out a little bit. One thing I wanted to note here was I heard them on I think it was the Go Time podcast or one of those. Seth Fargo was there. I'm trying to think he's VP of product or something like that. Anyways, he mentioned that they can actually support a sustained rate of 25,000 requests for secrets out of a T2 Micro on AWS to with Vault, which is written to Go. So it's pretty astounding what it's able to achieve. And it doesn't stop there, right? You've got databases, time series databases, FluxDB that was written on this. It's originally written on VoltDB as its underlying database. They've since changed that. And I'll finish off by saying these guys at Reconfigure.io are actually developing a Go-based software development environment, and we actually had them at our DevFest event to talk about this, and I've recorded that. If anybody's interested, contact me. They're going into a private alpha right now with this programming environment. What you're allowed to do there is basically an Amazon F1 instance, which has I forgot exactly how many cores. It's a relatively large machine and multiple FPGA cards plugged into PCI Express slots. You're able to actually take the Go program and selectively target it to run on the FPGAs as acceleration, or the CPU cores, and kind of move that across the boundary without a lot of impedance in how you write the code. So quite a collection of projects there. So our gopher in that corner here has every reason to be proud based upon the adoption, and there's a lot more. So now I want to just launch into like some of the projects I've done in the past with IDM. Now, what I would say is that what you're looking at here is the PowerMac G5. And I actually purchased one of these maybe a year and a half ago for 150 bucks. So it's long in the tooth. It's a really old machine. But what I did want to point out was to draw an analogy to concurrency and parallelism is this bottom statement down here in this review of the machine. I don't know if you're familiar with processor and Northbridge chip architecture, but the processor, to speak to peripherals, has to talk over the front side bus to like PCI Express, and graphics cards, and things like that, right? So in this case, at the time that this was created, it was kind of a pretty fast machine, 2 gigahertz, and they got up to 2.5 at one point. We're way beyond that now, obviously, but the front side bus was operating at a 2-to-1 rate with regard to the processor frequency, which at the time only hypertransport was coming close to that. So here's the architecture in some abstracted sense that kind of gets that done. So you see that the interface between the PowerPC 970 and this block in the middle, U3. So this is a Northbridge chip. These are the peripherals in PowerPC 970s, obviously the processor, right? What you see is a 64-bit bus, basically between the 970 and the U3 chip. And essentially in the way that it's commonly known, people will call that a parallel bus, right? I mean, if you talk about parallel and serial buses, that's what you're thinking about. That's a parallel bus. There's 64 bits. They're all operating in different traces on the board going between the chips. It's parallel. Well, in fact, there's a whole lot of coordination going on to make sure there isn't any error rate on any of those bits, that the delay on the clock receiving those bits is exactly right, so that it goes in the center of this eye diagram you can see there at the bottom of the top red box. So you can see those openings that exist, right? That's the data transitioning on the bus. The clock has to essentially be a sufficient amount of signal to noise ratio, within that window for the receiver to say it's 0 or 1 coming into the Northridge chip or going up into the processor. And the way that it achieves this is by very highly optimized receivers and drivers on both the processor chip and the Northridge chip. You can see them as RCDR and DDR there. And also, I would point out on both sides of this, you have a per bit delay. So, based upon the board trace of the bits kind of coming across the printed circuit board between the chips, the elastic interface, the EI block in the U3 chip, will actually go ahead and put a variable amount of delay to ensure that the clock and the data I actually line up nicely. So, as you can see, people call this a parallel bus, but there's a huge amount of coordination that goes on, and if it goes wrong, you get corrupted data. So this is concurrent operation, right? Same thing goes for this other structure down here, which is basically an asynchronous FIFO. Okay, so very similar to the concept that you brought up earlier, where you're thinking about channels as not being a queue. Well, this actually is a queue. It gets filled by the processor and drained by the peripherals essentially, and vice versa for like PCI Express goes back up to the processor potentially, right? But the idea there is that even though you would think, well, that's highly parallel too, I just shove stuff into it as long as it's full. That's the catch, right? As long as it's full, it can be drained. Again, the very basic things associated with thinking that this is parallel fall apart when you think about the fact that it has to. It does have to be full, and it has to have a particular packet in it that PCI Express or graphics subsystems will recognize that they have to process. So there's some coordination going on. So I would argue that most things that we consider to be parallel are really concurrent if you look hard enough. What we're looking at here is actually the switching chip in a Cisco Stackwise Catalyst ASIC that I worked on while at IBM too. I did jump say timing closure on this chip. And I don't want to dwell too much on this one here, but barring the name, which is kind of interesting, there's another kind of creature on the board too that this cooperates with called the Yeti. Turns out, so these guys are pretty funny when they name their chips. But I just want to launch into the system level view. So you look at a networking switch, right? So basically the way these things operate is that over here is the data interface, and here are the ports that you would plug into to do networking, right? So the idea is that you would be able to take this and stack it essentially with other ones and plug them all into these counter-rotating rings on the management interface. And it would function as if they're a bigger and bigger switch as you buy more and more of these 1U or 2U packages. And each one of these actually has a multitude of these switching chips in it, because the goal of these Strider chips is actually to take a look at the destination and so forth of the packet that wants to get to another place in the network, and kind of forward it on the proper port so it can get to the next location. And that sounds parallel too, right? Can anybody think of one reason why, like, kind of sending an Ethernet frame through some of these ports to another destination in the data center versus doing the very same thing on a port right next to it through the switch? Needs to be concurrent. Okay. The reason is because there are several, but the most interesting one, I think, it's kind of subtle actually, is that these switches actually support voice over IP communication. So they support quality of service, which means that essentially a packet with a higher priority and latency is a packet that's stringent, has to get to its destination, or you drop some of the voice in the call. It does head-of-line blocking for anything with lower priority. So even with a simple layer 3 switch, it looks parallel, but in fact, if you zoom out to the system level or even a feature within the chipset that supports it, you find out that there's point coordination where you hadn't thought about it. Some other things like, when connectivity meets the application, you might be doing link or port aggregation between two ports, and they both have to actually operate appropriately to get the kind of bandwidth that you want. Now, that's probably going to function fine if one of them drops out. And the other thing is, well, what if there's a big loop around, whereas one of the inputs was a control for an application, and one was data, and you needed both of those to actually operate. So again, concurrency at the system level. Everybody recognize this logo? Shout it out. Everybody knows. Watson, right? Exactly. So, any guesses how? Are you guys familiar with Watson kind of winning against Jeopardy, or sorry, against Ken Jennings in Jeopardy previously? That was about 2011 time frame. Yep. Well, any ideas the size of the machine that was needed to get that done? There it is. It's 10 racks worth of Power 7, processors. There's actually 2,880 threads of computation in there. So pretty big machine, to kind of get that done. And there's the result, right? So one thing I can say is, Ken did get to lounge nicely in the T.J. Watson Research Center auditorium, where they had to bring the Jeopardy set to kind of, play this game. But I guess my point is, if you're looking for something people would consider to be parallel computation, well, this is probably it, right? And there's probably some level of parallelism in here, but likely to be that the algorithms running on there also have points of coordination, concurrency too. So it does scale out for sure, and it doesn't become a problem that's easier to solve with time. So this is something that I grabbed from the industry news just a couple days ago. I guess it's basically the same set of racks. They probably had to rack out some servers with some chips died or some other things like that along the way, but since 2011 until today, they may have changed out into Power 7 Plus, which is kind of a die shrink, and put some accelerators, onto the multi-chip module, but it's still performing well in terms of AI. I understand if you scale this down by a factor of 24, though, that's the current Watson that you see them advertising in the H&R Block commercials. So it's a little bit more, I guess, user-friendly as far as purchasing these things. So here's the processor roadmap, and I just wanted to show you the PowerMac G5 that we looked at earlier was a derivative of the Power 4 architecture. As you can see the time frame I showed you was, I think, 2003. So this Power 4 was essentially the 2001 version, and it was used as a baseline starting point to make the PowerPC 970, which was in the PowerMac G5. Steve Jobs was very excited about that design when it came out, as far as its graphics performance and ability to render. And his Worldwide Developer Conference, he's extolling his virtues. But things moved on, right? Power 5 was made Power 6, Power 7. What may not be immediately obvious is that basically Power 6 was kind of a step back in time. So Power 5 was essentially an out-of-order execution machine, superscalar out-of-order execution machine, and also had two-thread simultaneous multi-threading, right, in each core. So Power 6 actually kept the two-thread simultaneous multi-threading, but did away with the out-of-order execution. So everything was issued in order, was retired to memory in order. There was renaming, obviously, to keep the pipelines full, things like that. But it was quickly recognized that the Power 6 was not going to scale in terms of anything but frequency, because its power level and its heat generation were tremendously high. So that's where we get into the Power 7 design here and 7 Plus that I mentioned, which are the heart and soul of Watson supercomputer that we saw, I think, even to this day. Power 8 is actually a processor architecture where that company Reconfigure.io I mentioned earlier kind of got their start in terms of introducing their technology. I won't go too far into that, but they're working on Power 9 and introducing that now too. I would like to dwell a little bit on the parallelism that's inherent in the Power 7 microarchitecture, right? So how many people here are into processor microarchitecture design? As far as instruction sequencing units, fixed point units, branch predictors, and stuff. Maybe I'll race right through that then. I mean, this is just basically, I've underlined some of the areas that I worked on when I worked on our submarine architecture. So I have some insight into that. We can talk about that later if you're interested, or I would understand if you're working on your projects and you want to get into that. I just wanted to point out here that there's a large amount of hardware concurrency management that goes on in one of these superscalar machines that the program is never going to see. So the idea of having, at the deepest levels, an understanding of what the machine is doing to execute your instructions is really tough to do when you get to this level of complexity. Because there could be 8 fixed point units, chunking away, and 4 floating point units chunking away in any given clock cycle. Some of these instructions are multiple clock cycles, some are single. Some are blocked based on a memory access or GPR rename. There's so many things that can go on to keep you from making progress in your project or in your program that are kind of abstracted from the program. So I just kind of wanted to launch into a project that, now that we've covered the hardware aspect of things and got a feel for parallels and concurrency, I just wanted to launch into a project that I put together a while back, which essentially takes a number of, should we say, like water control devices. So the idea here was not to concentrate on the device being managed, but more so to show the concept of social and civic IoT. So it's easy to get a board like the Arctic 10 or a particle photon chip to control a GPIO and turn a valve on and off and read a water measurement, which is kind of what was going on here. So I thought, well, maybe it makes sense to wrap that in a bigger concept, right? And say, well, how can we enforce some kind of policies in terms of an organization's use of water, right? How can we, encourage reclamation, use of reclamation water or runoff or desalinized water? How can we take an individual from one organization at one part of a state and another person at another organization or house in another part of the state that both feel like they want to conserve water where maybe their families don't, and get them to get together so that they can reduce water consumption overall, kind of a cup at a time, as I would say. So as you can see, I'll describe a little bit here. Basically, there were two, like the hardware architecture, there's 2 Arctic 10 boards. One was running RethinkDB, the NAT server, and the other one was running a custom Go server that I kind of sanitized the code on so we can take a look through it. And I'll do that after this. But those are talking over Wi-Fi to a bunch of particle photon chips, which are running NAT's Arduino client. And so those are responsible for every time, a certain amount of time expires. If the, if water is being used at a particular point of use in the house, broadcasting to the server, hey, I'm on, track my usage, right? So the whole idea is to be able to inventory the usage of water over time, determine kind of who's using it in the house, and square that up with regard to the policy, and then allow those people to interact with other people that are doing the very same thing, either within their community locally or remotely. I got another diagram later that shows this. And the point of interaction is through the mobile apps, which I put together with the Ionic framework. React Native wasn't really well accepted at that point in time. Yeah, you can read this if you want. I went over most of this stuff. So here's the idea. So what you see here is you've got an org 0 and org n, basically, right? So in other words, there's organization 0 through n, right? So they could be any number. And within each organization, you've got, at the top, you see, like on the left-hand side, D0 through DI, for example, right? So those are the water devices. So those are the ones which are, that's the point at which you're turning on the device and tracking its uses when it's on, right? The actual flow through it. And at the bottom, you see those phones in U0 through UJ, for example, on the left, right? Those are the users in the organization. So those are actually the people that are kind of authorized to use those water devices. Of course, there's a guest account too, and various things like that we can get into. But the idea is that in the middle of all of that, there's organizational goals. So, org 0 says we commit to saving or using a certain amount of water, right? We don't want to go over that. There's some incentives, social and monetary and so forth, that you could loop into this too, ultimately. So say that whole model is stamped out over here in Organization M, and there's multiple places where this is going on. Well, the idea is that if somebody in there kind of wants to overachieve and do a little bit more than the rest of the family members to maybe ensure that mom can get an extra shower, or who knows what, right? You know, do something benevolent. The idea is that you could form a remote civic or social community where you could extract some benefit from doing that based upon social positive feedback in social networks. And there's also the opportunity to participate in a local civic or social community. People in your like your town or city, right? So that's the whole idea, is to try out this concept. And that's a little bit of a complicated diagram. We don't have to get into that. To show you some example code. Just quick. I sanitized it quite a bit so that we could. Can you guys read that? Okay. So now I'm not going to run any of this stuff right now, because the primary reason being I've got to have a NAT server running. I've got to have my Rethink DB three Rethink DB instances running for 2 out of 3. High availability. There's a lot of dependencies. So I'll just go through and describe. Because I do know this. I've run this through. It runs just fine. I just tried to put it linearly in this file so it's easy to understand. So basically what we're looking at on the top there is, so we're in a package called Ripple at this point, right? So that's the name of the project. First structure that you'll see, and Bill brought up structures earlier with his server struct. That was the last thing that I put together. Was that right? Was it a struct, Bill?
No, I'm sorry.
Okay.
Yeah.
You want me to change the file? Okay, all right, cool. So on the initiator in this case is the user. So I thought this would be a little bit general purpose, which you see, any place you see initiator, it's a user. So the use in the diagram previously. And any place you see provider, it's a device, water device, okay? As I mentioned, I thought there was a pattern here where it's generalizable, and to some extent it is, but it's confusing, unless you have that mapping. So the initiator basically has an ID, and basically an ID key, which is what Rethink DB has in it when it stores. It has a cryptic string that it stores it as, so that's why there's 2 IDs in there. One's human readable, the other's database generated. There's a tag associated with it. There's a field for whether or not the person's an admin. So can they or can they not affect the policy or override things, right? So kids can't, parents can't, for example, that kind of thing. There's a location key which tells you what room in the house it's in. That's a string. There's a WD using. So for every person, you're only allowed to use 1 water device at a given point in time. That may be the case that you could make the argument they may be able to use more than 1. They're reaching out, brushing their teeth, and showering or something. But for this sake of argument, we say there's only 1. Collaboration partner field is if they are doing joint chores with their family members, like their siblings. The idea would be that they would get some additional points for that. So the whole idea is that if the collaboration is going on, the collaboration partner string is set to the other user that they're collaborating with, and it's a 2-ended connection. And then there's a reward DB pointer, and that's yet to be defined yet, but that was what I was talking about with regard to an external database, which has a pointer to all of the rewards that they currently have available to them to get reported back to their mobile app based upon reaching certain thresholds. The providers, so each of the water devices themselves have an ID, an ID key, a tag, a location, which is understandable. A state key, so state being it's in request mode, it's on, it's off, and so forth. We'll see those states later. State context key, initiator 1 key. So that's like user 1 and user 2. So 2 users are collaborating with a water device. Those will get populated. That's that 2-ended matching I was talking about. Whether or not the thing has a civic feature is indicated by the civic feature key. Whether it has a collaboration feature, like a dishwasher, is a water consumption device that you can collaborate around. Somebody can unload it, somebody can load it, it uses water. So the idea is that if you get that going on, you should reward those kids for doing, chores without being, kept to do that, right? And whether or not it has a reclamation feature, which means can it draw from a reclamation tank to salinization water versus fresh water, that kind of thing. What you'll see below each of these structures is are essentially receiver functions. They'll show these earlier too. Essentially, a structure becomes kind of like quote unquote an object almost, when you attach one of these receiver functions to it. In this case, we're attaching is we took a design concept that Rod Pike talked about in 2011, I think it was, lexical scanning, we call it. And what he did there was use some of the kind of sort of limited compared to some functional languages. Ability of Go to operate on functions as first-class citizens, and so you can pass them as arguments, return them, and so forth. That allows us to actually construct something which operates like a finite state machine in this case. So you can imagine for each of these water devices, when it's waiting and ready to be initialized, waiting a request, when it's running, when it's off, and so forth, it's doing different tasks, right? And if anybody's studied FSMs in either hardware design or in software, you'll realize there are certain conditions at which you kind of move through those states. As and in this case, there's only 4 simple states. Well, what's going on here is that if you see the type that's defined at the very top is actually an FSM state function, and that is essentially the function that's going to get passed around as an input, kind of into a particular function and returned from the function to determine kind of which state you should go to next, okay, as you're progressing through the states in the finite state. The structure right here, which is an FSM in struct, is actually all of the kind of input information you should send into the state to tell it whether or not it should actually make a transition or not. And I won't go through kind of all the fields here, but really quickly, I mean, like the init string actually is so when you first bring up the emulation, the database has all of the saved state for each of these water devices. It pulls it in and saves it into essentially a string that gets fed into this. So the structure is actually aware of all of its kind of critical initial information, and as it's updated in the database, it's repopulated. So it's always got all of that context. The RDB session is the Rethink DB database session handle. So the initiator themselves, that's actually so this contains a structure like initiator that we saw up above. It actually also has a slice of all the providers, which are all the devices. So, to some extent or another, then the user knows exactly who they are and what their state is by the string, the init string, and they know all the water devices available to them to use, right? By storing both of those. And you'll actually see there's RxFE and TXFE message channels in there. And we talked about channels earlier as a way to signal to a particular Go routine, whether it should continue to make progress or block. And essentially, RxFE message means it's getting a received message from the front end, so from the mobile application, or it's transmitting TX to the front end application. So there's bi-directional communication there, essentially. What we're seeing here, basically, is I'll just go down to the provider state machine. You see the same structure here, right? Again, there's the prop FSM state function, which is what gets passed around as it makes state transition. And then there's the prop FSM instruct, which is just like what we just looked at, but has more features to it, right? So it has the GPIO on the board. It's whether or not it's being emulated or not. The Arctic 10 switch tells it whether it's emulated or not. If it's being emulated, it actually pulls from a time series database and mocks what the physical device will do. If not, it's actually literally attached to a flow meter and it's measuring flow. So there's an ability to control that on a per device basis this way. And this is also taking messages in from the NATS bus regarding, basically kind of water readings and different things like that. So you'll see RX NATS message and TX NATS message in there too. Otherwise, it looks very similar to the one that we looked at previously. Here's some more helper functions to initialize GPIO on that, to change the setting on GPIO and to finish, which means to return the GPIO to the original settings prior to the emulation, right? And here are the kind of the functions that are, again, I've removed the body from the function, but the idea is that the initial state for any water device is that it's waiting for a request. Once it gets a request, it goes to prob FSM state on, which is that second function down. The third function down is prob FSM state off, right? And then, so basically, you think about it this way, it's waiting to be used, it's in use, it's done and reported out, it's information to the database, and it's ready to be requested again, essentially. So those are the states that it has to kind of transition through. And what you can see there is that it turns out that the primary way in which it makes progress through all of these states is by changing those channels, that what's going in over those channels in each of the structures that I said were like inputs to a finite state machine when it should make transitions. So you'll see like, it's hard to point to, but right here. So just imagine a point at the very top one, because they're all the same. So if it gets something coming in on FSM in RxFE message, so if the front end application said that it should do something, it then fires that into Rx string, which is a local variable. I didn't define everything here, but you get the idea. So once Rx string comes in and gets populated with something, then essentially what it does is it then parses what it finds from the string and determines kind of how to make progress based upon field analysis of the fields. And so essentially that's kind of just stamped out multiple times to represent how it should get from one state to the next and back around to request. Like I said, the code's missing, but believe me, it's a lot cleaner without it. So I just wanted to get the context behind how this is like architected, I guess. So the function at the top right now is actually it's the run, a water device FSM, let's say, right? So basically what you do is you pass in a pointer to the provider FSM in struct that I mentioned, and essentially it will then look across, so it'll start at the state, prob FSM state hint. We didn't look at that, but that was one of the state before request. So if that returns is not nil, then it was, basically populated correctly. It'll then go and actually return. So it'll go into a loop where it basically then returns whatever state should have been returned based upon what you sent in as the struct and what you were sending in over the channels in the struct that you sent in and whatever they were seeing. It'll make transitions. And every time it makes a transition, there will be a return statement, and it'll say either stay in the state or go to some new state. And then that will become the left-hand side state variable. And then again, that will go back up into the for loop, right? And you keep kind of making progress. As long as you're not in state in it, you're going to stay in that loop and keep on making progress. So it's maybe a little bit hard to kind of visualize, but what's going on here, and I don't want to get too deep into this, I guess, but each organization in those blocks that I showed earlier has a number of water devices that basically open a WebSocket to the mobile application. I'm sorry, the organization itself, just for simplicity, opens a WebSocket to the mobile application. And this particular WebSocket listener that we're looking at right here will essentially take all reads and writes from the mobile application and from NAPS, essentially send those in, just from the mobile application, and send those in and bring those back to, send those into the devices being emulated in a piece of code that we've yet to look at, and then also get values back, and send them back out through the WebSocket, kind of to the mobile app, because you can imagine that you have to control and update the UI as things are progressing to determine when you should turn buttons on or off, or record particular usage levels and things like that. So, and the next thing down is just kind of opening up essentially a web server for the mobile application. That's that listen and serve function right there. So, I won't get into these details too much. I mean, these are just basically the WebSocket readers and writers. There's some interesting stuff in here with regard to the select statement, but it's a lot to get through. So the initiator-provider interaction is where all the emulation takes place, right? So basically when you hit that setup WS listener for org 0 and 1, ultimately what it does is it puts a bunch of information about the users in the house, the water devices in the house, the quotas, all kinds of stuff, and puts that into a closure. So it's in scope for the WebSocket listener, essentially. And then you basically return an upgraded HTTP handler back, and that forms your WebSocket connection. But this is the, basically all of the emulation logic, and the logic that actually connects with physical water devices in here. Again, I don't know if I want to kind of go through all this detail. I mean, there's quite a lot of things going on here. The most important point to take away is that for organizations 0 and 1, they're both, multiple organizations are supported, and water devices may either be emulated or they may be physically attached, real devices that you're monitoring and control. So you'll see in here there's a lot of channel construction, initialization, there's various different connections to NATs based upon the code associated with the device. As far as RethinkDB is concerned, you'll see the NC1.subscribe line is very cryptic. Prefix indicating that first thing's a sprinkler, next one's a shower, and so on. So fairly pedestrian stuff that's kind of just sample repeat, things like that. So the whole idea is that you go through the provider slice essentially, and which is initially a zero, correct me if I'm wrong, zero capacity slice, and I keep appending to it and increasing its capacity for every device in the family, because I can't know ahead of time how many there are. So the idea here is this flow loop actually will go through the provider slice. So initially it's of capacity 0 and has nothing in it, and it's of 0 length, so it can't accommodate anything. But then what I end up doing is just basically kind of creating some variables that I then use to sort of initialize it here for every single trip through this for loop. Yes? Sure. Yeah.
By seeing that you were using channels to kind of drive a state machine,
Yes.
so it's inputs coming in, different sensors,
Right.
network.
Yep. And inputs from the mobile application.
Triggering state changes.
Right. Yeah.
Signaling data to those channels.
That's right. What was that last part?
You just signaling data to make state changes.
Correct.
The state machine is driving everything else that's going on.
Yeah, it's making changes through the states in terms of whether it's a request on or off. Yeah, exactly.
It would be really cool if you should put a smaller example together.
Yeah, I know.
State machine could be driven through
Yeah, I can do that.
events like that.
Yes.
That would be really fun to see. I can see anybody use
Well,
channels.
yeah, I mean, this is Rob did put this to use in lexical scanning. I think that token analysis that he did. This is a different application, but same idea.
Use channels.
Yep.
when he's doing-
Oh, I don't know. I have to think about that. He did use the input structure.
Yeah.
Okay. Yeah, I can put an example.
But it would be fun to see. And then I would ask why there's no conversation. It would be fun to see an example, a smaller example, to see state machine change.
Oh, definitely.
Because that's what you're doing here.
Yeah. The whole idea here was to just show kind of a more, I guess, extreme implementation of some of these basic concepts. But you're right. I think something that sinks in a little bit easier is a more extreme example.
This is a bigger code base. But
Yep, I can probably do that, yeah. So, yeah, there's not too much more here, really. Just kind of go through with the people in the house and do kind of the same thing. And then, basically down here, what we've got is we're kicking off a bunch of Go routines to actually run these finite state machines that we've set up, right? And they essentially, kind of run appropriately. I don't know how many there are going to be, so I could do some counting to the weight group based on that to synchronize, but, it does not exit because I have a walking for loop at the end of the thing, right? That's not the most ideal solution by any means. But, so, like I said, I just wanted to kind of go through some of that, just give you some idea about how to model a concurrent system. To your point, maybe I'll put a smaller example together. So,
that would be fun to see.
yeah. So, any questions? Sorry, ran over a little bit.
Did you write this all yourself?
I did have some help on the project. The two of us working on it. There's a lot of interesting concepts in here that I wanted to kind of get my arms around. So this provided a unique example. And I would mention, was in the Open Power Foundation, and still am, and did have access to a Power 8 machine previously, and this runs fine, Power 8. I just wanted to mention. It's pretty cool. Great. Thanks for your attention. Appreciate it.